In this lecture, we're going to take a look at how we can use the integration techniques we've developed to calculate the amount of work done by a system. So to do that, we're going to have to start by coming up with a physical or mathematical definition of exactly what we mean by work. So to do that, we're going to take two factors into consideration. First, we're going to say that if we apply a constant force to the object, then the work should be directly proportional to that force. And second, we're going to look at the distance the force moved the object. And again, just thinking intuitively about this, moving the object a greater distance should mean a greater amount of work, so the work done should be directly proportional to the change in distance. All right, putting these two things together gives us our starting formula for work based on a constant force. Work equals the magnitude of the force times the change in distance. Okay, so before we move up to the situation where we have a non-constant force, let's think about the constant force situation graphically. If the force is constant, that means its graph is a horizontal line. And we're looking for the work done by that force as it moves between 2 points. Now, notice that this formed a rectangle, whose width is delta x and whose height is f. That means the area of the rectangle is f times delta x, which is also equal to the work. In other words, for a constant force, the work is equal to the area of the rectangle under the force curve. Okay, so how can we use this geometric interpretation to step up to the non-constant force situation? So to see how this will work, take a look at this situation here. We have a variable force, and we want to know the work done by it between 2 points A and B. So to do this, I'm going to break the interval up into n pieces and draw rectangles over each of those intervals. Now, hopefully, at this point, this is looking pretty familiar. The area of each rectangle approximates the work done by the force over that interval. So if I add up the areas of those rectangles, using the function values at some point on each interval as the heights, I'll get an approximation of the work. And if we take the limit of both sides, as n goes to infinity, we get a formula for the work done by a variable force. The left side, which doesn't have an n in it, is just w, and the right side becomes the integral of the force function between the two intervals. And there's our formula. Okay, so let's see how we can use this in a couple of examples. So first we'll start with a really very simple case. Suppose the force pushing horizontally on an object is given by f of x equals 3x. In other words, the force increases linearly as the object is pushed. How much work is done moving the object from 0 meters over to 3 meters? Okay, we've got our formula, right? And I'm going to put 3x in there for f of x, and we're going to do this integral from 0 to 3. And very simple integral. This is 3x, 3 halves x squared. We evaluate that from 0 to 3. We put the 3 in and we get 27 halves, the 0 in and we get 0. So the magnitude is 27 halves, but what are our units here? Well, our formula essentially says it's force times distance, right? Well, so force is measured in newtons, distance is measured in meters, so just brute force, we're just looking at the units of the component parts, the units should be Newton meters, and that's fine. That is the SI unit for force, although this is usually written as a joule being equal to 1 Newton meter. So let's look at another example here. This one is a little more complicated. I'm assuming we have a 10-foot deep funnel, and it's filled with oil that has a density of 50 pounds per cubic foot. And I'm going to assume that the slope of the sides of this funnel are given by the equation y equals x. So it's a 45-degree angle. And I want to know how much work will be done lifting all of the oil out through the top of the funnel. Okay. What makes this interesting is as we go down into the funnel, we have less and less oil that we have to move, right? Because it narrows as it goes down. But we're moving it through a greater distance. Okay, so how can we put these two factors together? Well, I'm going to use an approach that should be very familiar. I'm going to look at a slice, a narrow slice taken out of the center of the funnel. Now remember, in cross-section, the funnel is a circle, right? So this shape here I have, if you looked at it in 3 dimensions, it would be a cylinder, right? And I know how to calculate the volume of a cylinder. And if I multiply that by the density, the number of pounds per cubic foot, I'll have the number of pounds. And that's the force that will be required to move that slice up out of the funnel. Okay, so I'm going to assume that the height of my slice here is delta y. I'm going to assume that it's y, or feet, are measuring in feet here, that it's y feet up from the bottom. And that means that the radius of this cylinder is also going to be y units, because that side is given by that equation y equals x. All right, that's enough for me to calculate the total force, the total weight of that section. Right? The change in force to move that piece is going to be 50 pi y squared delta y. Okay, so let's break that down a little bit. Pi y squared, that's the area of the base of my cylinder. I multiply that by the height, delta y. That gives me the volume of the cylinder. Then I multiply that by 50. That's the density of the oil. And that gives me the total force that's going to be required to move that particular piece around. Okay, so to turn this into the amount of work required, I need to know what distance I have to move it through. Well, I have to move it from y units up all the way up to the top. Well, that distance is going to be 10 minus y. So this means that the change in work is the force times the change in distance, the change in force times 10 minus y. But my change in force, that's that 50 pi y squared delta y expression. So I'm going to put that in for delta F. And now I have a formula for the amount of work required to move that little slice up out of the funnel. So to get the total work, I'm going to add up the slices. If I let delta y if I let delta y go to 0, it turns into an integral. Right, this integral here. I pulled the 50 pi out in front, and then left the integral from 0 to 10. That's the height of the funnel, times the y squared times 10 minus y. And now it really is a relatively straightforward integral for us to calculate. I distribute the y squared. That makes this the integral from 0 to 10 of 10y squared minus y cubed. And we apply the power rule for integrals. And we get this for the antiderivative. And we substitute in 0 and 10s. Putting 0 in, that just gives us zeros across the board. If we put 10 in and get a calculator out, it's a practical problem, so we'll go to a decimal answer. We get 130,899.69 foot-pounds. Or we're doing this in imperial, non-metric units. Right, so what were our units? Well, the unit of force is a pound, and the distances were given in feet. And so our units will be foot-pounds, right? And there's our final result. Okay, so in the next lecture, we're going to continue this thread here. We're going to look at some more examples, see how we can use this formula to calculate the force in a couple of different situations.